One line from the Bruce Lee movie Enter the Dragon is applicable to today's world a lot. Strength makes all the virtues possible. For India to be stronger, it's high time that we think of innovation. We have been doing great service for the last 30 years, and our institutionalized education has designed us to be great service people. That's fine, but it's high time that we think of innovation. We live innovation, and we have to create an atmosphere where we all can say, if it is difficult, I'm going to do it. So let's do the difficult. Let's start by simplifying some of the, I would not say difficult, but interesting concepts. What about quantifying wisdom? So let us take one scenario. Imagine someone doing PhD and he's engrossed in his work. He's trying to find some answers and suddenly his mobile beeps and he sees a Facebook notification. He gets triggered and he starts an online fight and he loses the track of time and ends up losing the direction as well. In the evening, he sits quietly to understand where did he go wrong. And then he understands that if he would have neglected that Facebook notification, things would have been much better. So what will he do from now on? He will switch off the notification of Facebook when he is working on his things. Now, this brings us to a very important concept of backpropagation. So his thoughts shaped his belief, or rather understanding, and then those will be implemented in the future. This is what backpropagation is in a simpler way, if I can put it like that. One of the most important concepts that enables this backpropagation is gradient descent, and we are going to learn gradient descent in this video.
Do we need gradient descent? As I already mentioned, that we need it for backpropagation neural networks, we need it for support vector machines to reduce or to minimize the margin between classes. For linear regression, we need it for minimization of the mean squared error. For logistic regression, we need it for binary cross entropy loss minimization. We need it for NLPs, GANs, encoders, several things. So let's go for gradient descent. Before we start, let us recapitulate few of the things that we learned in school. That derivative at a point on the curve is nothing but the slope of the tangent at the point, as we can see. And one point also I would love to mention here, that calculus is way more than formulas. It's a philosophy, and someday I would love to discuss the philosophical interpretation of calculus. Let us go back to class 11 and recapitulate local maxima and minima. First, we equate the first derivative with 0, and then we solve for x, we get the points, and if the f double dashed x, which is second derivative, is greater than 0, then it is local minima. If it is less than 0, then it's local maxima. If it's equal to 0, then we have to go for advanced tests to identify the point of inflection, if it is present or not. Okay. Now, if we look into the curve, we'll observe that at x equal to 1, there is a local minima, right? We can find this using gradient descent as well, because gradient descent is nothing but you take a point in the curve and then you slowly walk down the curve till you hit the local minima. In other words, till you reach a point where your first derivative tends to 0. Now you can tell me that what's the need for gradient descent if we can use local maxima or minima? What's the need for gradient descent? Let's now look at the second curve. This is a curve which is sine 5x by x plus 0.1x. For this curve, applying the local maxima minima method would be very difficult. So we'd use gradient descent successfully here.
And there are several other curves which are way more complicated than this. So now you understand the value of gradient descent. We'll take a simple example and understand gradient descent in the next section. Let's look at this function. X to the power 4 minus 4x squared plus x. This function would roughly look like this, and we have to use gradient descent to find a local minima. Now let us look at the formula that we are going to use for descending. So this formula is x new is equal to x old minus alpha f dashed x old. So we are going to take the derivative and multiply it with alpha, which is a parameter which determines how big a step we are going to take to descend. Imagine you are at the top of a hill and you are trying to climb down, but it's so pitch dark that you can't see anything below. So what you do is you take very small steps and try to touch the floor. When you see that there is no, I would say the steepness is not there anymore, then you kind of assume that you have reached the flat surface. Similarly, we will try to use this concept for gradient descent. And here we would use a formula. Maybe in some next sessions we would understand in depth about this formula. Now, this is our fx and this is our gradient descent formula. Now, alpha, the value we have taken is 0.01, and you can cross validate this particular parameter, but it's usually the standard, so you can start with this and play with this and see how it affects your algorithm, and it's all fun. Now our first value for x is 2.5, and this is just for demonstration. So we see that we have got f dash 2.5 as 43.5, x new is 2.065, then we calculate f dash of 2.065, calculate this, and then we continue this process. We can see that we are the f dashed value is decreasing, and if we continue to do it, it will converge to a value which is kind of 0, which will the f dash text was kind of converge to 0, and then we'll observe that we have reached a local minima. As you can see in the red, that we have reached a local minima, and this is the curve. Now one problem you can see here is that there is another minima for the curve, but following this methodology we would not reach there. So another minima which is, I think, better in minimizing the cost function exists. In other words, global minima can be overlooked in case of gradient descent, and we'll find ways to solve it. Now the next question is, when do we stop the gradient descent? Well, if we look here, there are a few criterias and we can mix and match those criterias, as these are pretty self-explanatory, that if the function is converging to a 0, the change in the function is converging to a 0, if the number of iterations are reached, and if the value of x is converging to 0, the absolute value, then we would stop the gradient descent. Saw the beauty of gradient descent, and gradient descent helps us find the local minima for very complicated functions which are used as cost functions for machine learning algorithms. Still, one point that we need to address is that how can we find a global minima? Well, perhaps in the next sessions we'll discuss that, and we'll try to solve this perhaps shortcoming, and then we'll try to explore more horizons. Take care.